about for PET and the production. Obviously, we do have a generator that we use for PET. Does anyone remember what it is?
Oxygen.
No.
It's accelerated,
And the germanium?
No.
Germanium?
isn't it? Question?
No. I'm sorry, what did you say, Ashley?
What kind of generator?
Rubidium? I don't know how to say it right.
Yeah, you're right, you're correct. Okay, it's the rubidium generator. Okay, so it's the strontium-82 rubidium generator. Okay? And in order to make the strontium-82, they actually use molybdenum. They take molybdenum and they bombard it in an accelerator with protons, 700, 800 MeV protons, and then that produces the strontium. Okay, then from the strontium, when it decays, now what's the half-life of strontium? 82.
Isn't it like 58 days?
Close. That's about 25 days. Okay, so strontium 82 is 25 days. And it decays by what method?
Beta plus. Phosphorus.
Isn't that beta plus?
Beta minus?
Well, the rubidium 82 decays by beta plus, but you got to.
So
Yeah.
beta minus.
So, well, the thing too is this, okay? As a result of the generator having a 25-day half-life for the parent and 75 seconds
52.7 day half-life.
for strontium 82,
Yeah.
No, that's
Strontium
89.
is 52.
well, we're looking for 82 strontium. Okay. Strontium 82 is a 25-day half-life. The daughter has a half-life of how long? What's 82 rubidium?
You should say 25 days.
Isn't it 1.25 seconds?
It's 75 seconds.
1.25 minutes.
Yeah. Okay, so you have a parent that has a half-life of 25 days, a daughter that has a half-life of 75 seconds. So what type of equilibrium is that? Remember the equilibrium that we talked about? We have transient and we have secular.
Well, then 75 and what one? It's transient.
But, okay, actually says transient. Sing, what do you say?
I have no idea. I don't know what to guess.
Secular's 1,000, isn't it?
Okay, well, basically, transient is 10 to 100 times. Secular is 100 to 1,000 times plus. So it's going to be secular. Most of the generators are secular. Technetium molybdenum generator is one of the few transient. Now, in the old days, the technetium generator was the only one that we had. So transient equilibrium was the big one back then. But see, now we have the rubidium krypton generator, we have the strontium rubidium generator, and if you remember, that was one of the things that because of the strontium emitting a very high energy radionuclide, that's some guy who had a heart study going through the radiation detectors in Canada set off an alarm. Okay.
So when the molybdenum is bombarded with protons, what's thrown out? What's ejected?
You know, I needed to look at that because I was trying to find the reaction. I was looking at
So there must be another element in that, because it goes from 99 to 82.
yeah, there's got to be a something really big difference, because I was looking at it and the lowest isotope that I found of molybdenum was about 88. So, but I don't know. I mean, it didn't make sense to me by looking at it, but basically that's what they were saying.
So it's not molybdenum,
That's
not,
mine too.
that's not being bombarded to make strontium.
No, it's another isotope of molybdenum. Okay, but anyway, so the first thing that they talk about is the generator system in the pet production. And so again, some of the things that you need to be prepared for or be aware of is that the strontium is made in a particle accelerator, and when it decays, we have a 25-day half-life for the parent, a 75-second half-life for the daughter. So we have secular equilibrium. And when they're eluting the generator, remember that with 99 molybdenum technetium, we use normal saline. Okay, we also use normal saline for the rubidium generator. We use air for the rubidium krypton generator. Okay, so you need to know what materials are that they use for elution. With the rubidium generator, you're going to be administering about 30 to 60 millicuries. Okay, so in other words, because it has such a short half-life, you're going to be constantly infusing the patient during the time that you're doing the study. And so if you're doing a pharmacologic stress study, they typically have the adenosine being pumped in on one arm and the rubidium being pumped in on the other. The nice thing about this is that almost immediately, 10 minutes after you wait a while, you can go ahead and do the rest study, or do the stress and the rest within about 10 minutes of each other. Problem is the generator is about $30,000. You replace it every month. So if you're doing a lot of heart studies, it's a good deal. Okay. Yeah, the other thing another thing that we talked about was the cyclotron, and this is what I was going to be kind of showing you with a slide presentation. I think I showed this to you way back when. We were talking about quality control of radiopharmaceuticals. Basically, the radiopharmaceutical quality control that we do for technetium products is almost identical to what we do for PET products. Okay, so basically it's all about the same stuff. Some of the other little things here, we're going to be taking a look at the construction of a cyclotron. And actually, why don't we just go ahead and do that. What I would like you to be familiar with, again, are the reactions for making radiopharmaceuticals. So for making fluorine-18, basically we take water, and instead of having an isotope of 16 oxygen, we substitute 18 oxygen. Okay, so it makes it actually pretty expensive. When we bombard that as a PN reaction, and we, again, remember, this is the target, this is the bombarding particle, this is what's emitted, and then this is the product. Okay, so you should know, sort of offhand, what the different reactions are here. On page 4 of the PET study guide, it kind of gives you a summary of the half-lives of all of the different PET radiopharmaceuticals that we use. Right now, the big ones that we're using are the carbon palmate and carbon acetate for myocardial imaging. These are fatty acids. We're using 13 nitrogen in the form of ammonia for myocardial imaging. Actually, they actually say that this one is one of the best ones, the nitrogen. Oxygen 15, they're not really using it a whole lot, but they're just either giving it to the person either to inhale or injecting it in the form of water. I haven't really heard anybody using this too much because with a 2-minute half-life, there's not much you can do with that. And then, of course, our mainstay right now is fluorine-18 that we're using for metabolic studies of the heart, brain, and tumor imaging. Okay. Let me kind of go here to our audiovisual extravaganza. I got this from a talk that was given in Las Vegas by a guy from Stanford. Stanford has a big meeting up there every year, and you know, it's really kind of fancy. But so this is what it looks like up there at Stanford. If you ever want to have an experience, there's a thing called Zillow. Have you ever? Zillow.com. It tells you what the prices of houses are. A friend of mine bought a house up there. It's about 900 square feet. The thing is worth like $1.4 million.
Still needs some of that.
Oh, It's it's.
Okay.
I mean, it's not even a. It's unbelievable the prices.
900.
Okay, so what we're going to talk about is FDG synthesis, the type of equipment, okay, quality control, and some of the stuff that's coming down the horizon for this. Okay. Okay, this is what the cyclotron looks like. Usually it's very heavily shielded, 2-foot thick walls. Here you can see the Ds. They typically, as we said, we take protons. Now do you remember, how do we get protons for deuterons?
Water,
Oh my goodness, no.
hydrogen.
Okay, you take hydrogen gas or helium gas, you pass it through a spark, that removes the electron, and now you have a charged particle. So in the case of a hydrogen atom, remember it only has one electron. I hit it with an electric spark and remove the electron, and what am I left with? A proton. Okay, so that's where we. So if you ever go to a cyclotron, you'll see these cylinders of gas that provide, you know, our material for making the protons and deuterons. Deuterons, or remember hydrogen 2. And we also have helium, or we call it alpha particles. It's basically helium gas with the electrons removed. Now, one of the things that we have to be careful of is making sure that we only shoot in the correct, you know, in other words, if I'm shooting protons in, I want to make sure that I'm only shooting either in a proton and not a deuteron. So what's the process that I use to remove undesirable radionuclides from both my target and also from the gases that I'm using to make the bombarding particles? Remember that there's other isotopes that are mixed in. It's not all just, you know,
Diffusion by weight or something?
that's part of the process, but the actual thing where I actually remove the undesirable radiant or undesirable atoms. You remember the term enrichment?
That's how they made like uranium-235, right?
Yeah. Now, enrichment is where you remove the undesirable isotopes, both in the target and in the bombarding gas atoms, so that you get what you want.
How was that done, with like a box with a little hole in it, and the ones that are heavier will stay behind?
Yeah, well, what they did with uranium was they vaporized it, and then they had it pass through a membrane. The lighter uranium atoms would pass through faster. So after a series of these things, they got it from about a 2% concentration up to a 98% concentration. It only cost them $3 billion back in World War II. I mean, back in the 1940s. But it sure made a heck of an explosion, didn't it? Okay, but that's what they had. You know, when you guys are making stuff in a cyclotron, it's very expensive, because to enrich the gas that we use, expensive. To enrich the targets, expensive. Because again, remember, if you don't get out those other atoms, you're not going to produce the desired radionuclide. Okay, this is what a D looks like. And this thing here, this is part of the D. In the center is where the gas comes out, and then it passes through a spark. You can probably not see it very well here, but there's an electrode that removes the electron. And then they alternate the charges on these Ds. So once I remove the electron, the proton now has a positive charge. So on one D, I'm going to put a positive charge which repels the proton. On the other one, I'm going to put a negative charge which attracts it. So I'm pushing and pulling the proton. And again, they alternate the positive and negative charges on here at about 50 million times a second. It's about 50 megahertz. They use a radio transmitter to make these things change to positive and negative. Okay, and so what happens is, okay, so it gets pushed and pulled over here, and then as we keep doing that, it starts getting more and more momentum and speed, and then it starts taking a longer and longer course. And then eventually I have a guide over here that attracts it. I have a little negatively charged plate, and then I attract it and run it down these tubes to the target. Does that make sense? So that's how we're able to do it. That's actually kind of pretty, isn't it?
Copper?
It's all copper. You know, people are stealing copper like you wouldn't believe, right? I've had guys get electrocuted not too long ago. Okay,
For
and then this is
stealing that,
our, huh?
You got electrocuted for stealing that.
Oh, no.
Copper.
There was a-
Steel
Power wires and
stuff.
stuff. That's what got electrocuted.
Or they've even taken down like phone cables.
It's awesome.
Yeah, just out here in Highland, some guys broke into a,
Construction side.
no, it was an actual transmitting station, you know, electrical transmission. So they both got killed, which, you know.
I don't know if
Some point.
I don't know if you heard this story where this guy was trying to steal copper wire and he had to go under the fence. He accidentally butt dialed 911 and he got caught while he was doing the copper in his truck.
Yeah, we get it. We catch them all the time at construction sites. Okay. Well, anyway, this is the reaction. This is the one that we're most commonly using is the isotope of 18 oxygen. And basically, we use water. You know, water with 18 instead of H2O with 16 oxygen, we put the oxygen 18 in there. So basically, the proton knocks out a neutron, and so that's how we're able to get it. Okay. Normally when they bombard any targets, it's going to be anywhere over 11 million electron volts up to about 33 million electron volts. But for making fluorine-18, they use 16.5. Does anybody remember why we have to have at least a minimum of 11 MeV to shoot that particle in there? Yeah. What's the binding energy of most nucleons in an atom? What is the amount of force holding protons and neutrons in an atom on average? No. No. Okay, it's about 8 MeV. Okay, on an average, it's about 8 MeV. The lower radionuclides are less, but you know, on an average, it's about 8 MeV. So you have to overcome that 8 MeV nuclear binding energy and the positive or the charge of the electrons and protons to shoot that proton into the nucleus. Remember that like charges repel, so if I shoot that thing in at 11 MeV, it'll overcome the positive nuclear charge. That's how we do it. Okay? This is an interesting thing, that the particles are traveling at this acceleration, 19% the speed of light, 128 million miles per hour. Yeah, that's pretty fast, right? I mean, if you were traveling to the sun is what, 77 million miles? What is, how come you guys don't know all this
I know the
trivia?
moon.
Yeah, okay. Takes about 7 minutes for light to get from the sun to the earth, so Okay, but anyway, the momentum, because it's such a small particle, it's like a mosquito crashing into you at that velocity there. So, I mean, it sounds horrible, but this is what the target looks like. Basically, your water is going to be in here. Well, okay. This just hooks the accelerator tube so that it can hit the target. The helium entrance window. Okay, this is again depending on if you're using helium or hydrogen gas. This is where it comes in, and this is where they put the water on the inside of that. So basically, the water comes in, it's bombarded, and then it goes out. This target gets very hot, so they have it under pressure. They also have it cooled because you're talking. I don't know if you've ever seen an electric spark and what it does when you're welding something. Okay, it gets really, really hot. Okay, these targets that when we bombard them, they get really, really hot. So you have to make sure that they don't explode or melt or anything like that. So typically they're cooled with water. Okay. Now this is what we start with when we do the synthesis. For the FDG, what we basically do is we're going to remove this and replace it with the fluorine. So we have these synthesis modules that they use, and this is what our final product is going to be over here. Okay. All of these radicals over here are removed and replaced with hydroxyl radicals. That's our sugar molecule. Okay. Okay, and then this is what the reaction looks like again. So we take our precursor, we add the fluorine to it, we get FDG, fluoro-FDG, and then these are all of the byproducts after the reaction. These are contaminants that we really need to make sure don't stay in our product when we inject it into the patient. Okay. So this is what goes on in that synthesis module. This is what the module looks like. And they have them for all the different radiopharmaceuticals. Okay. You guys seen these before? Okay. If you were making F-dopa, if you were making sodium fluoride, or in this case here, if you're making FDG.
Do many hospitals have this, or do they just get it from somewhere?
Well, if you have a cyclotron on site, then you probably have these.
How rare is that?
Huh?
How rare is that?
Actually, there's more and more of them. I know in Los Angeles, there's probably about 4 hospitals that have their own cyclotrons.
In all of LA?
Yeah.
Ones you say what?
Well, UCLA has one. University Hospital has one. Yeah, well, University Medical Center. I mean, they're right next to USC, LA County. I know Stanford has it. But most of us rely on, like, Cardinal Health, you know, because Cardinal Health has a cyclotron that they manufacture this stuff, or they have one of those pharmaceutical company, or one of the hospitals use theirs to make it. But basically the stuff just comes in and it automatically goes through all the reactions and then it comes out as labeled FDG. It's all automated because a person working in there would get a horrible dose. When I used to take my students over to the UCLA cyclotron, the people who worked there got super, super high doses. They had wrist badges, finger badges on every finger.
Seriously?
Oh yeah, every, but now it's all automated. And then this is what the tubing looks like. I mean, basically, like I say, the radioactive water that's now been turned into fluorine comes in here, and then stuff is injected and removed and all that kind of good stuff. So, like I say, it's, you know, this is another So, basically, the people don't have to get exposed to radiation anymore. Now, again, remember, we have to make sure that the stuff that we make is in the proper chemical valence. So what is this standing for? Okay, it's actually thin layer chromatography. So we make sure it's the proper valence, okay, before we put it on there. And so remember, here's our bound, and here's the free. So that's how we estimate the amount of tagging that took place. And in Ann Steve's book, there's a good little section on that, right?
Is that the one where you get the paper and you put it in that?
That's the easy way to do it. This one here, they actually have like a micro reader that reads the strip. But most of the time, yeah, you put a drop of your radiopharmaceutical at the origin, you put it in the solvent. Remember, we usually use like water or normal saline as a solvent, and also acetone as a solvent, because we're looking for two components. We're looking for free technetium, and we're looking for hydrolyzed reduced technetium. Okay? Same thing is kind of true here, except here we're just, again, looking at the amount of fluorine that didn't bind to the FDG. Okay? This is your origin here. It's scanned with a micro radiation detector, and so it basically shows you any blips here are contaminants. Here's your main product here. Okay. The other thing is, because of the other chemicals that are present in the reaction, you have to find out how much of those are there, because these are toxic substances, so they have to, this is what this residual solvents thing is here. They do like a spectrometry on it, and they can tell you how much of the, whatever solvents are that they used to get the product.
Acetone or...
Yeah. Well, maybe because, like I say, for some of these other chemical reactions like hydrolysis and things like that, you add other chemicals. So you want to make sure that those aren't present when you inject this into the patient. So that's what this part is for here. Chemical purity. What would chemical purity be? What would chemical purity be if we were talking about a molybdenum technetium generator?
Aluminum.
Okay, aluminum. Yeah, any of your non-radioactive components, okay, whatever other stuff that's non-radioactive, how much of that would be in there? That's what the cryptofix thin layer chromatography is for. Okay, because you remember with our technetium generator, use that.
The ethanol solution.
Well, that's the one where we use the pink. We have the pink stuff, the orange tricarboxylate paper. Okay, we put a drop of aluminum on that, and it turns really pink. Put a drop of our technetium eluate on there. Hopefully, it doesn't turn pink at all. Okay. So that's what this thing here. Okay. Now the radionuclidic identity. When you put it in the dose calibrator, and then you time the rate of decay, what are they actually measuring here?
They're seeing if there's any other contaminants like molybdenum.
Well, remember, we're talking about FDG now. So, obviously, yeah, with technetium. Okay. Well, what would be the contaminant that? I'm trying to think of what. Can't really think of any other radionuclidic impurities you would have with FDG, but what they're actually doing here is, if I measure the rate of decay, what should the value be, or what percentage should decay after a period of, let's say, a minute? Well, let me go back here a minute. Okay, I put my sample in here, I measure it, and then I measure it 1 minute later, and what am I actually looking at? What aspect of our radiopharmaceutical are we, well, the half-life, but if I'm not measuring it for 110 minutes,
Fraction of the
yeah, but what do we call that fraction of the half-life? Huh?
Chemical decay.
fraction of the
No.
half-life.
No,
You're such-
Okay, the rate of decay over time, what do we call that? Not half-life. Okay, if I had 100 millicuries of technesium, and 1 hour later I measure it, how much would I have? Yeah,
Well, 6 hours, so 6, 100, and 1 hour later. 6 hours.
okay, Mr. Singh, what part are we measuring here? If I had technesium, and I had 100 millicuries when I put it in the dose calibrator, and 1 hour later it measures 89 millicuries, what did I just measure? The which one?
The decay factor?
Okay, yeah, decay constant. Okay, remember the decay constant is the same, 0.693 divided by the half-life. So when I put this into the dose calibrator, I can measure it 1 minute later and know exactly how much activity I should have if fluorine-18 is present. Does that make sense? Okay, because otherwise, I mean, if I waited 110 minutes, then the half-life is, half of the stuff that I just made is gone. So by knowing what the decay constant is for 1 minute, I can put it in here and immediately tell if I have the right radiopharmaceutical. Is he bothering you?
No, I cracked my neck and it hurt.
Oh, I heard that snap. I heard a pop. Okay, so that's one way. The other way is to put this in a spectrometer or a multi-channel analyzer and look at the energies of the radionuclides given off. Okay. Now, what's this thing here?
Horseshoe crab.
Okay, it's a horseshoe crab. So, what are we looking for here?
Pyrogenicity.
I'll tell you, my mother-in-law. Okay.
Is it pyrogenicity? That's
Okay, it's pyrogenicity. Okay, so we use the what is it that we're actually?
Oh, we use,
is that the blood or plasma turn
Yeah.
a certain color?
Well, normally the blood of this crab is clear. Okay, and if there's any endotoxins, it gets cloudy. It gels up. Okay, but it's the amoebolysites of the horseshoe crab that we're using. Okay.
What's the name of this class, the second class? This is
What's
titled.
topics of nuclear
It's-
medicine?
Well, the first one is that's RT381. This is just, I think it's just called PET,
Okay.
I think. But again, this is the same stuff that we use for technesium. Everything that we just talked about is the same thing that we use for technesium. Okay, but again, remember crab blood is your pyrogenicity testing, right? Okay, if a product is sterile, is it pyrogen free?
No.
Right. Because remember, if you have little pieces of bacteria in there, it can still be causing fevers. In the old days, they used to inject 3 rabbits and monitor their temperature. Okay? But then now we have the pyrogenicity of the ALA amoebolycite of the horseshoe crab, which, like I say, is a lot faster. Okay, the pH. Remember, the pH should be somewhere around normal blood
7.
pH. Yeah, that's anywhere between 5 and 7, somewhere around there.
So
Okay.
even if a crab is sterile, it's not pyrogen free?
Yeah, because you can still have dead bacteria in there. You know, it's like when you get a vaccination A lot of times they inject you with dead bacteria or dead virus, but you still get a fever. Okay, your body still reacts to it, so you can still get a fever from it. Because there's also sterility too. Sterility and pyrogenicity are two different things. But anyway, so here you have the pH testing. Usually this is litmus paper. Litmus paper? Okay, I don't know. Then here again, this is using the multi-channel analyzer. I don't know if you can see that very well. There's a red thing down here. Can you guys see that?
Mm-hmm.
Okay. This shows you all of the different, like here's your peak of 511 keV, and then here's some stuff down here. This is a backscatter peak. The other ones you don't see down there because they're very low energy. But, you know, so that's the multi-channel analyzer. Okay, sterility. What you're looking for, there's a couple of ways of doing sterility. Basically, you can culture it in different types of medium, or you can also put it in with radioactive sugar, carbon-14 labeled sugar, and if there's any radioactive carbon dioxide produced, then you know that there's living stuff in here. So little air bubbles and radioactive carbon dioxide 14 gas. Just like the H. pylori test. You know the H. pylori test where you have the patient drink the
It's like
carbon.
carbon-14.
Yeah, they use carbon-14 labeled sugar. And
What's the half-life of carbon 14?
it's, I want to say, I think it's like 14,000 years. I'm not sure.
How is that safe to use people?
Well, it's such a low decay or low emission of decay that it doesn't.
What's the dose like from Mike? How much do you
Yeah,
get?
I know it's
It's
a
tiny.
It's very, very small. I'm not really. If you look under, look under shackets. But as far as the half-life goes, I want to say it's about 14,000 years. I don't remember for sure. Mr. Andy, could you look it up for us quickly?
What were we looking for?
The half-life of carbon-14.
1 mic for the dose.
Okay, it's 1 microcurie.
57-30 years.
Okay, 57-30 years.
57-30 years.
Okay.
I think the other one, 14,000, isn't the archaeological carbon dating. What's that, carbon-12?
It should be the same. No, carbon-12 is, I think, stable. Yeah, it's carbon-14. Yeah, that should be, so 5,000 years is,
5,730 plus or minus 40 years.
oh, okay.
That's minus 40 minutes.
But anyway, so the thing here is, with you look for changes in the medium. Like here, you can see that there's this area here that changes pink. Also, the formation of carbon dioxide and things like that.
What's in there? What's that broth?
Well, there are different broths that they use.
Is that chicken or pork?
Glyphosate.
That's what I understood.
So just anything that gives it a chance.
Yeah, it's the, sometimes they'll have like blood agar in there. I'm trying to remember what the other ones were. They have one for growing fungus. But the thing is that most of the time, unfortunately, if you use this method here, by the time you realize that it's been contaminated, it's too late because it's already been injected into the patient. So all you can do is have the technologist call the patient and do a follow-up. And are you still alive? Okay, you're good. Okay. The other thing is, you remember a long time ago I showed you that we had this thing called the millipore filter? Okay, the millipore filter is how we provide sterility, for materials that can't be gassed or heated or anything like that. So we pass it through the filter unit here, which is the millipore filter, but in order to make sure that the filter is okay, you have to test it. And the way that they test it is they pull on, they hook the filter to a solution over here, and pulling it through a syringe the pressure on the inside of this thing should go up. I think it's like 30 psi or something like that. And that means that there's no holes or tears in the filter. If there's holes or tears in the filter, the pressure won't go up at all. It'll just stay down. But any type of, you'll see this for a lot of different types of devices that we have to ensure sterility. Okay? So this is one of our sterility tests, is by checking the filter that the FDG has to pass through. The other thing is, as you remember, you do a visual inspection, hopefully behind the L block. Remember your L block? That's your radioactive or radiation protection glass. Most of our solutions are clear, so you shouldn't see anything at all. The only exception is what? Okay, MAA should look cloudy. Okay, but if it has any other colors than that in there, then you got a problem.
Sulfur collate's clear too?
Yeah. Yeah, because the particles are so small. That's why even when you put it under the microscope, you shouldn't see it. Okay, so if you see colors in there that are not supposed to be in there, then that means you got bad stuff. Right?
And then after the shine, we're supposed to check that it's not cloudy.
I think so, yeah. There's, what you need to start doing is collecting the package inserts from different radiopharmaceuticals and look at what the criteria are. Okay. I mean, it's like when you make MAG-3, you know, and they talk about injecting air into the vial. Okay, you need to understand why did we do that, or what was the purpose of doing that, things like that. This is what a typical day at Stanford looks like. 3 a.m. you start the bombardment. Okay, you bombard it for about 2.5 hours, about 2 hours. And then this is the synthesis part where you put it through those automatic tubes. And then you ship it out. Okay. You do the quality control and dispensing is about an hour, and then it goes out to different facilities. Okay. In Cardinal Health, notice that they start about 11 p.m. at night, and you're doing about 3 different runs. So this is your early morning FDG, this is your mid-morning, this is your late afternoon. Cool, huh? It's a good job. You don't like to sleep. Yeah. You like to sleep at night. Okay. This next thing here, we've got a whole bunch of different positron emitters that are coming down the hoop here. Most of them are going to be using fluorine. Okay, but over here we have an 11 carbon. Over here we have I think this is F-DOPA. So we're looking at neurotransmitters and peptides and things like that that we're going to be using in the future. But again, these are these synthesis modules that they have for each different radiopharmaceutical that we're making. I couldn't tell you what everything does here, but the biggest challenge is probably making sure you have all these wires or tubing hooked up properly. It's kind of like on the inside of your car. Okay, this is the carbon-11 module. Again, to me they look the same. I couldn't tell you what any of those things are, but all I know is that when they're making the radiopharmaceutical, you could probably get a lethal dose of radiation if you were standing anywhere near this thing. Okay. They were, at the time at Stanford, or when they gave this meeting, they were trying to show how important it is to be a radiopharmacist. And the problem now, it's kind of like medical technology. When they used to have a medical technologist draw your blood and count the red blood cells, it really isn't rocket science anymore. It's kind of like going to your grocery store. The grocery store people are really upset because they're no longer considered a professional. You can basically take anybody in there and have them scanned.
Was considered professional back then?
Yeah. And you had to type in the numbers on a grocery clerk made more money than we did.
Get out of town.
they made triple time on the holidays, yeah, they made more money than we did. But, see now, anybody can scan those product codes. Okay, but anyway, so these are just some things that they're, you know, the quality control testing, again, pH, visual inspection, radiochemical purity, thin layer chromatography, and again, not only think of it for your PET radiopharmaceuticals, but also for your technesium. So again, you're going to be checking for free and also hydrolyzed reduced stuff. Okay. Radionuclide purity, which means there's no other contaminants. We all know that with technesium we have to look out for molybdenum contamination. With FDG, I'm not really sure. I mean, if there's other materials in the target, you're obviously going to get other radionuclides created. We know that with strontium rubidium generators, you have to be careful not to have any 82 strontium or any 85 strontium present. Yeah, I think you're allowed 0.02 microcuries per millicurie. Specific activity. What is specific activity? This goes way, this is from the first semester, guys. It's not activity per ml, we'll tell you that right now.
Activity, the concentration?
No.
So we have,
Ashley, what's specific activity?